Okay, in this lesson we're going to talk about polynomial functions. We're going to start off with talking about some vocabulary review, and then we'll get into talking about connections between the equations and graphs of polynomial functions. Okay, let's start off with a monomial. Okay, a monomial is a term that is a number, a variable, or a product of numbers and variables. Okay, some examples. So this column here is going to be examples of each. We can say the number 6, the variable x, or the product of those two, 6x. Or we can make it more complicated. We can say negative pi x y cubed z, and all that is still just a monomial. So by the way, these variables can have whole number exponents, so no fraction exponents, no negative exponents for a monomial. All right, some non-examples. So these are non-examples of monomials would be something like 1 over x. Okay, no variables in the denominator. We can say the absolute value of x. We can have square roots. What else? And then let's do something with exponents. So maybe x to the negative 3/2. That can't happen either. Okay, so non-examples of monomials. Okay, next up we have polynomial. Okay, polynomial is a monomial or a sum of monomials. Okay, so a monomial is just a type of a polynomial. Okay, you guys remember studying binomials and trinomials and that sort of thing in the past. So let's see, we can do 6 is a polynomial because it's a monomial. We can do x squared plus 6, or we can do something like 3x to the 5th minus 10x squared plus 4. That's also a polynomial. Okay, and then for non-examples, if we have, let's say, a polynomial over another polynomial, okay, so that's no longer just a polynomial, that's a rational function. Or we could throw in something like some other kind of function, like a log. A log, let's try that again. Okay, so like the log of a variable. Okay, so the log of y. Okay, that's not a polynomial. All right, so next up, standard form. Okay, standard form is when terms are in descending degree order of a polynomial. Okay, so an example of a polynomial in standard form is 2x to the 4th minus 3x cubed plus x squared minus x minus 10. Okay, so that's in descending degree order. Okay, a non-example might be something like 5x squared minus 3x to the 4th plus 1. Okay, let's talk about why that is or is not in standard form. Okay, so let's look at our next term, the leading term. Okay, the term with the highest degree. Okay, so if we look at our last good example, this guy right here, the leading term is this whole 2x to the 4th monomial there. Okay, and we know that because to find the degree of a monomial, what we do is we take the sum of the exponents of the variables. And then, since we're dealing with not just monomials but other types of polynomials, we want to find the degree of any polynomial. Then we take the largest of the degrees of the monomials in that polynomial. All right. So the degree of this monomial here, this 2x to the fourth, is 4. Okay, the degree of this next term here is 3, and the degree of this quadratic term is 2. The degree of this single x is 1, and then any constant has a degree of 0. So you can see that last example is in descending degree order. We went 4, 3, 2, 1, 0. This guy here, this non-example, the degree of this guy is 2, and the degree of the next one is 4. So we want to go from biggest to smallest. You guys know that. All right. A non-example of having a leading term would be this guy right up here. Okay, so we would want to rewrite this so that our negative 3x to the fourth goes first, our 5x squared goes second, and then our 1 comes last. All right, let's look at end behavior of polynomial functions. If you were to graph a polynomial function, similar to what you've done with linear functions, quadratic functions, and power functions, which you've already done, all those are subsets, types of polynomial functions, then there's some patterns with the end behavior. Okay, so if we look at two different components of our polynomial functions, if we look at our leading coefficient and if we look at the degree of our polynomial functions, and we can tell something about the end behavior without even graphing it. So if we have an odd degree polynomial function, then we know that our end behavior is going to be opposite of each other. Okay, one end is going to be negative infinity, other end is going to be positive infinity. Okay, which one's which is determined by the leading coefficient. If it's a positive leading coefficient, then you're going to go from negative infinity to positive infinity as your x's get larger. And if you have a negative leading coefficient, it's going to go the opposite direction, from big to small. Okay, if you have an even degree polynomial function, then your end behaviors are going to be the same on both ends. Okay, so if it comes from positive infinity, then it's going to end at positive infinity. Okay, your y's on the ends are going to be going the same way. Okay, with a positive leading coefficient, up and up, with a negative leading coefficient, down and down on both ends. Okay, so let's look at the another important characteristic component of polynomial functions, the zeros. Hello. Okay, so if f is a polynomial function and x minus c to the m power is a factor of f, then c is a zero of multiplicity m. Okay, so new term here, multiplicity. So if we've got a factor x minus c, so we've got our standard form of polynomial functions, which we talked about up here. We've also got another form, which is factored form, which we're going to see in just a second. And the benefit of seeing the factors is that we can see, number one, the zeros, and then kind of what our graph's going to look like right around those zeros. Okay, so in this first example, it says find the zeros and their multiplicity of the following functions. All right, in number one, we've got f of x equals x plus 2 to the third power times x minus 1 to the fourth power times x plus 5. Okay, so the first thing we want to do is we want to pull out the zeros. Okay, remember zeros are the x-intercepts, they're the roots, the solutions to this equation. So the first one, if we convert this to subtraction, we've got x minus negative 2. So our first one's going to be negative 2. We're going to have a root at negative 2. And the multiplicity of that root is going to be 3. Okay, because that is the exponent of that factor. Okay, again, this only works when you're in factored form, not in standard form. Okay, your second root is going to be a 1. Taking that from our second factor. And its multiplicity is a 4. And then our last root, for this was a subtraction, that would be a negative 5. So we've got x equals negative 5. And the multiplicity of that root, we've got that invisible 1 exponent that's always lurking there in the shadows. Okay, so multiplicity of 1. So pulling out the zeros and the multiplicities given factored form. Okay, so why do we care about the multiplicities? What's the benefit of finding that? Well, the graph of a polynomial function will cross the x-axis at zeros with odd multiplicity, and it will touch the x-axis at zeros with even multiplicity. So looking at whether a 0 is odd or even can tell us something about the graph. It can tell us whether our graph's going to cross or touch at that particular 0. Okay, so let's sketch this function by hand on this graph right down here, knowing the multiplicities and the zeros of this function. Okay, again, without a calculator, we could graph this in a calculator and see what it looks like exactly, but we're just going to give a sketch. Okay, so first off, looking at our roots, we've got a -2 root. So I'm going to come down here, put a point at -2 on my x-axis. Second one is at +1. And then our third one is at -5. Okay, the multiplicity of our -2 root is 3. So at this -2 root, our graph is going to kind of look like a cubic function. It's going to cross because it's odd, but it's going to kind of have the same behavior right around that root as a cubic function that also has a multiplicity of 3. Okay, so I'm getting ahead of myself a little bit. Let's go back and let's think about where is our function going to be coming from? Is it going to be coming from positive infinity or negative infinity? Okay, so we can look at our function itself and say, well, what's our degree of the whole function? Okay, if we add all of our exponents, 3 and 4 is 7 and 1 is 8, then the entire degree is going to be 8. Okay, that's an even-powered function, so we know our end behaviors are going to be the same. Okay, I don't have any negatives in front of my x's, so it's going to be positive. So I know my end behavior is going to be coming from positive infinity on both sides. Okay, so function is going to come down towards -5, and our -5 root, if we work from left to right, is going to have a multiplicity of 1. So it's going to look like a linear function going straight through. It's going to cross through that -5 there. Okay, it's going to come down. I don't know how far it's going to come down, but I know it's going to come back to hit -2, and it's actually going to cross again because that's a multiplicity of 3. So I don't know how far down that's going to come, but I know that it's going to come up and it's going to kind of flatten out as it gets to -2 because, again, that multiplicity of 3 makes it look like a cubic function right around that 0. Okay, and then at x equals 1, it's got a multiplicity of 4, so it's just going to touch at 4. So I'm going to come up and then just come back down and touch, at 1, not at 4. And then we know it's going to end in an increasing fashion. So there's our sketch of f of x. Again, not exact, but knowing from our overall degree, our sign, and our roots and multiplicities, we get a good idea of what that graph is going to look like. Okay, you guys do g of x, number 2, in your notes. Okay, find the roots, the multiplicity of each one, and then give it a good sketch. Okay, so let's do another one of those from beginning to end. So given a function in factored form, in our next lesson we'll look at doing the same thing for polynomial functions that are in standard form. We'll save that for our next lesson though. Let's stick with factored form for these. We're going to find these characteristics and use those to sketch this graph. Alright, so let's start with degree. Again, if we were to multiply these out, if we were to multiply each of these binomials out, this one 3 times, this one 2 more times, multiply those together, we would have a degree of 5. So that's our overall degree. It's positive because we don't have any negative signs in front of our x's. Okay, so positive, odd degree, I know that my end behaviors are going to be opposite. I'm going to come from somewhere down here and I'm going to end up increasing as x is increasing. All right, so let's look at our zeros next. So our first 0 is going to be 1. So x equals 1. And then the multiplicity is going to be 3. It's odd multiplicity. Our second 0 is a -5. Again, if you remember from solving quadratics, if we didn't have these exponents at all, and you got to factored form and you were trying to solve this or find the zeros, you would set each of these equal to 0 using the zero product property, and that would give you your roots in this case. Okay, same idea for these polynomial functions in factored form. All right, so we've got both of our roots. So if we go ahead and say, well, if this is 1, I'm going to have a root there and another root at -5. Okay, in behavior, so if we do our limit notation, so the limit of f of x as x approaches -infinity is -infinity, and the limit of our function as x approaches +infinity, as x's get bigger, is +infinity. Okay, again, looking at the sign of our overall polynomial and the degree. Okay, and then lastly, if we want one more point, then we can look at our y-intercept. Find the y-intercept, let x equal 0, and then simplify your function. So I'm going to plug in 0 into each of these x's. So I'm going to get 0 minus 1 cubed times 0 plus 5 squared. That's going to give me -1 cubed, which is -1. This is going to give me 5 squared, which is 25. So that's going to leave us with a y-intercept of -25. Okay, so we know it's going to contain the point 0, -25. So coming way down here, for time's sake, and again, because this is just a sketch, we can come down here, we can say this is -25.
Mr. Florio, could you come to the front office, please? Mr. Florio, could you come to the front office, please?
And plot a point down here. And let's do our sketch. So we know it's coming from -infinity. We're going to come up at -5, multiplicity of 2. We're just going to touch it. We're not going to cross the x-axis. We're going to come, I don't know how far to come down, but I know we're going to come back up. We're going to hit that y-intercept. And then at 1, we have a multiplicity of 3. So we know we're going to cross at 1. And because of that 3 multiplicity, it's going to look like a cubic, so we're going to flatten out a bit, and then I'm going to make it increase some over here. Okay, knowing that it's just going to get bigger. All right, so there's our sketch. Again, without using a calculator, by hand, using what we know about the degree, zeros, multiplicity, and behavior, and throwing in our y-intercept for one more point. Okay, so last kind of example, we can also go the other direction. If we're given a graph, let's see if we can analyze that graph and come up with some important information about zeros and whatnot for that graph in particular. So here's our graph here in green on our blue axis here, and the first thing we're asked to analyze is the degree. Okay, so to find the degree, this little unique thing you can do is you can make a vertical line anywhere that you see a turning point. Okay, so anywhere you see a maximum or a minimum or one of those kind of cubic little saddle points, draw a vertical line and then count how many sections that you just created on your graph. Okay, I created one section over here, a second one in the middle, and a third one over here. That means we have a degree of 3. Okay, go into our next one, sign of the leading coefficient. And again, that falls in line with the end behavior of our graph. We've got different end behaviors. Okay, the sign of the leading coefficient, it goes from small to big, so that's positive. Complex zeros, this is always going to be the same as our degree. Let's make that a different color. Okay, always the same. The number of positive zeros, looking at our graph, we don't have any positive zeros. Okay, no x-intercepts in the positive domain. Okay, negative zeros, we've got 1 right here, looks like at -2. Okay, but then notice we've got this guy here at 0. So we have a root at x equals 0. 0 is 0. And because it just touches, we're going to assume that's a double root, okay, with a multiplicity of 2. Okay, so that one it counts for 2 of these complex zeros, okay, because it's a double root. All right, imaginary zeros. What we do is we take our complex zeros and we subtract all of our positive, negative, and if we have any zeros. Okay, so 3 minus that 1 negative, and then this guy counts for 2 because it's a double, it just touches. So that leaves us with 0 imaginary zeros, or 0 imaginary roots. Right, and that's it. So we talked about, with our polynomial functions, we reviewed some basic vocabulary. Make sure that you're comfortable with finding the degree, with knowing what's a monomial, what's a polynomial, and what's not. Being able to identify a function as a polynomial function is real important. We looked at the end behavior of polynomial functions and sketching a graph from the roots, multiplicity of those roots, and then the reverse order of that, looking at a graph, coming up with some of the information, and then we could come up with a simple equation for this. We'll do that in a later lesson.